Welcome! In today's session, we will tackle LeetCode problem number 1013, partition array into three parts with equal sum. This problem challenges us to divide an integer array into three non-empty parts with equal sums. Stay tuned as we explore different approaches to solve this problem effectively. The problem requires us to work with an integer array called ARR, which consists of n integers. Our goal is to determine if we can partition this array into three non-empty, contiguous subarrays such that the sum of elements in each of these subarrays is equal. If this is possible, we return true, otherwise, we return false. The input is a single integer array, and the output is a Boolean value. This problem focuses on finding partitions with three equal sums, and the array elements can include both positive and negative numbers. Let's explore some concrete examples to clarify this further. In the first example, the input array is 0, 2, 1, -6, 6, -7, 9, 1, 2, 0, 1. The output is true because it is possible to partition the array into three contiguous subarrays with equal sums. Specifically, part 1 contains 0, 2, 1, with a sum of 3, part 2 includes -6, 6, -7, 9, 1, with a sum of 3, and part 3 contains 2, 0, 1, with a sum of 3. Since all three parts have the same sum, the output is true. However, this isn't always the case. Consider the next example. In the second example, the input array is 0, 2, 1, -6, 6, 7, 9, -1, 2, 0, 1. Here, the output is false because no matter how we attempt to partition the array, we cannot find three contiguous subarrays where all parts have equal sums. This highlights the importance of verifying not just the total sum but also the feasibility of dividing the array into exactly three contiguous sections with equal values. Let's look at one more example to reinforce this concept. In the third example, the input array is 3, 3, 6, 5, -2, 2, 5, 1, -9, 4. The output is true, and here's why: the array can be split into three parts where each has a sum of 6. Part 1 is 3, 3, part 2 is 6, and part 3 is 5, -2, 2, 5, 1, -9, 4. Each part sums to 6, so the output is true. This demonstrates that even with a mix of positive and negative numbers, it is possible to achieve the required partitioning under the right conditions. Now, let's discuss some critical constraints and key considerations. First, the array length must be at least 3, as each partition needs at least one element. The array size can be as large as 50,000 elements, so the solution must be efficient. The elements can range from -10,000 to 10,000, which means handling both positive and negative values is essential. Remember, the subarrays must be contiguous, and if the total sum of the array isn't divisible by 3, it's immediately impossible to partition it. Additionally, edge cases like arrays with all zeros or those with small sizes require special attention. Proper tracking of cumulative sums is vital to ensure correctness in these scenarios. To solve the problem of partitioning an array into three parts with equal sum, we considered a few different approaches. The first approach is the brute force method. Here, the idea is to generate all possible ways to partition the array into three subarrays and verify if the sums of these three parts are equal. While this method is conceptually simple, implementing it requires nested loops to check all combinations of partitions. This results in a time complexity of n cubed, making it highly inefficient and impractical for large arrays, especially when the size of the input can go up to 10,000. On the other hand, the optimized approach leverages prefix sums. The key observation here is that if the total sum of the array is divisible by 3, each partition must sum up to 1/3 of the total. Using this insight, we iterate through the array while maintaining a running sum, checking if we can find three such partitions. This method is much more efficient, as it avoids redundant computations and focuses only on the necessary checks. The optimized prefix sum approach has a time complexity of n, because it involves only a single pass through the array. Additionally, its space complexity is 1, as it doesn't require any extra data structures. This makes it the most efficient solution for this problem. However, another alternative is the sliding window approach. Here, the idea is to dynamically calculate the sums of three subarrays by using two pointers to define the boundaries of the first and second partitions. The third partition's sum is determined by the remaining elements. While this method can also achieve O(n) time complexity, it is more complex to implement and has more edge cases to handle. Compared to the prefix sum approach, it is less intuitive and requires more effort to debug. As a result, the sliding window method, while valid, is not as elegant or straightforward as the prefix sum solution. After evaluating the different approaches, we chose the optimized prefix sum method as the best strategy for this problem. The decision was based on three key observations. First, the partitioning condition relies on dividing the total sum of the array into three equal parts, which the prefix sum approach efficiently verifies using a running sum. Second, this method avoids the computational overhead of nested loops and multiple passes over the array, making it ideal for large input sizes. Finally, the prefix sum algorithm is simple to implement and has clear handling for edge cases, such as when the total sum is not divisible by 3. The aha moment came when we realized that the problem could be reduced to counting occurrences of 1/3 of the total sum as we traverse the array. This insight eliminates the need for explicit partitioning and streamlines the solution. Another important observation is that finding at least 2 valid partitions is sufficient, as the third part is guaranteed if the array's total sum is divisible by 3. When comparing the different approaches, the trade-offs become clear. The brute force method is easy to understand but impractical due to its O(n)³ time complexity, which makes it unsuitable for large inputs. The sliding window approach, while achieving O(n) time complexity, is more complicated to implement and debug, requiring careful handling of edge cases. In contrast, the prefix sum approach stands out because it achieves the same O(n) efficiency while being much simpler to implement. It strikes the right balance between clarity, performance, and ease of use, making it the most effective choice for this problem. By leveraging the problem's constraints and focusing on the key insight of dividing the total sum into 3 equal parts, the prefix sum method provides an elegant and reliable solution. In this problem, we aim to determine whether an integer array can be divided into 3 non-empty contiguous subarrays, each with the same sum. To start, the first step is to calculate the total sum of the array. If the total sum isn't divisible by 3, it's immediately clear that partitioning the array into 3 equal sum parts is impossible, so we return false right away. This step allows us to eliminate invalid cases early, saving computational effort. Next, if the total sum is divisible by 3, we calculate the target sum for each partition as the total sum divided by 3. From there, we'll need to track the cumulative sum while iterating through the array to identify points where the target sum is reached, signaling the end of a valid partition. These steps set the foundation for constructing an efficient solution to the problem. To find the partitions, we start iterating through the array while maintaining 2 key variables, cumulative_sum, which keeps track of the running sum as we traverse, and count, which records how many partitions with the target sum have been identified so far. For each element in the array, we add it to the cumulative sum. When the cumulative sum equals the target sum, it means we've found a partition, so we increment the count and reset the cumulative sum to 0 to start looking for the next partition. Once the traversal is complete, we check the count. If we've identified at least 2 partitions with the target sum, we return true because the remaining elements inherently form the third partition. Otherwise, we return false, as it would mean the array cannot be divided into 3 equal sum parts. There are a few key insights that make this approach both efficient and logical. First, the divisibility of the total sum by 3 is a critical early check, as it immediately rules out impossible cases. This ensures we don't waste time on further calculations when the problem has no solution. Second, tracking the cumulative sum as we iterate allows us to efficiently identify partitions without needing additional data structures, keeping the solution's complexity linear. Lastly, it's important to note that finding just 2 partitions with the target sum is sufficient. If the total sum is divisible by 3, the remaining elements of the array automatically form the third partition, making the algorithm both simple and effective. The use of basic data structures like variables for cumulative sum and count also ensures minimal memory usage, making the solution highly space efficient. Now let's address some edge cases that the algorithm handles. If the array has fewer than 3 elements, it's impossible to form 3 non-empty subarrays, so we return false immediately. The algorithm also naturally accounts for negative numbers, as the cumulative sum calculation doesn't depend on positive values. For arrays consisting entirely of zeros, the total sum is 0, and any 3 non-empty subarrays will also sum to 0, so the result is true. Regarding complexity, the time complexity is O(n), because we only traverse the array twice, once to compute the total sum and once to find partitions. The space complexity is O(1), as the algorithm uses only a few variables to track sums and counts, with no additional data structures required. This ensures the solution is both fast and memory efficient. Let's walk through a couple of examples to see the algorithm in action. For the input array 0, 2, 1, -6, 6, -7, 3, 2, 0, 0, the total sum is 1. Since 1 isn't divisible by 3, we immediately return false, as no valid partitions exist. Now consider the input 1, 2, 3, 0, 3. Here, the total sum is 9, which is divisible by 3, so the target sum for each partition is 3. As we traverse the array, the cumulative sum becomes 3 after the first two elements, marking the end of the first partition. After resetting the cumulative sum, we reach another 3, indicating the second partition. The remaining elements naturally form the third partition, so we return true. This step-by-step process demonstrates the efficiency and clarity of the algorithm in handling various scenarios. Here, we start by defining a function can3parts=sum inside the solution class. The first step is to calculate the total sum of the array using Python's built-in sum function. This gives us the sum of all elements in the array. Next, we check if the total sum is divisible by 3, because if it's not, it's impossible to split the array into 3 parts with equal sums. If the total sum modulo 3 is not 0, we immediately return false. After confirming divisibility, we calculate the target sum for each part by dividing the total sum by 3. We initialize current_sum to 0, which will help us keep track of the running sum during iteration, and parts to 0, which counts the number of valid parts we identify. Now, we begin iterating over the array. For each element, we add its value to current_sum. If current_sum matches the target, it means we've successfully identified one part. We then increment the parts counter and reset current_sum to 0 to start counting the next part. At this point, if we've already found 3 parts, we can return true immediately, as we don't need to check the remaining elements. If the loop completes and we haven't identified 3 parts with the target sum, it means the array cannot be partitioned as required. In that case, we return false. This ensures the function handles all possible cases, either exiting early when the condition is met or returning false after fully processing the array. This approach efficiently determines whether the array can be split into 3 equal sum parts by leveraging basic arithmetic and a single traversal of the array. Here, we begin by importing the necessary utility package and defining our solution class with the method can3parts=sum. The goal of this method is to determine if the input array can be partitioned into 3 contiguous subarrays with equal sums. First, we calculate the total sum of the array by iterating through each number and adding it to the variable total sum. Once we have the total sum, we check if it is divisible by 3 because, if it's not, it's impossible to divide the array into 3 equal parts. If the total sum is divisible by 3, we calculate the target sum for each part, which is simply total sum/3. Next, we initialize 2 variables, current sum to keep track of the running sum and parts to count the number of subarrays that meet the target. We then iterate through the array, adding each number to current sum. Whenever current sum matches the target, we reset it to 0 and increment the parts counter, indicating that we've successfully found one of the 3 required partitions. At this point, if the parts counter reaches 3, we return true immediately because we've successfully divided the array into 3 equal parts. This early return is an optimization to avoid unnecessary iterations once we've met the condition. If the loop completes without finding 3 partitions, we return false, indicating that the array cannot be divided as required. This approach ensures that we only traverse the array once, making it both efficient and straightforward. The algorithm relies on the fact that we reset current sum each time we find a valid partition, effectively isolating the sums of subsequent subarrays. By doing so, we can accurately count the partitions while maintaining a constant running sum. The method concludes by either confirming that the array can be partitioned into 3 parts or determining that it cannot. To solve this problem, we start by taking the given input array and calculating its total sum. In this case, the array is 0, 2, 1, minus 6, 6, minus 7, 9, 1, 2, 0, 1, and the total sum of all its elements is 9. The next step is to check if this total sum is divisible by 3. Since 9% 3 equals 0, we know it is divisible, which means it's possible to divide the array into 3 parts with equal sums. Now, we determine the target sum for each part by dividing the total sum by 3, giving us target equals 3. We then initialize two variables, current_sum, which will keep track of the running sum as we traverse the array, and parts, which counts how many parts with the target sum we have found so far. As we iterate through the array, we start adding each element to current_sum. For instance, the first few elements add up to 3 at index 2, which matches the target. When this happens, we reset current_sum to 0 and increment parts by 1 to indicate that we found one valid part. The process continues as we move through the array to check for other parts that also sum to 3. After finding the first part, we continue iterating through the array. When current_sum reaches 3 again at index 7, we recognize another match. At this point, we reset current_sum to 0 and increment parts to 2. As we move forward, we add up the remaining elements. Finally, at index 10, current_sum reaches 3 once more, marking the third match. We reset current_sum and increment parts to 3. At the end of the iteration, we check whether the number of parts found is exactly 3. Since parts equals 3, this means the array can indeed be partitioned into 3 parts with equal sums. Therefore, the function returns true, and the output for this example is true. In this example, the input array is 1, minus 1, 1, minus 1, 1, minus 1, 1. The first step is to calculate the total sum of the array, which is 1, 1 plus 1, 1 plus 1, 1 plus 1 equals 1. Next, we check if this total sum is divisible by 3. Since 1% 3 equals 0, it is not divisible. This means it is impossible to split the array into 3 parts with equal sums. With this early realization, we can immediately return false without any further processing, as the required condition of divisibility is not met. The output for this example is false. Now let's consider a new example, where the input array is 3, 3, 6, 5, minus 2, 2, 5, 1, minus 9, 4. We begin by calculating the total sum of the array, which is 3 plus 3 plus 6 plus 5, 2 plus 2 plus 5 plus 1, 9 plus 4 equals 18. Since 18% 3 equals 0, the total sum is divisible by 3, so we can proceed. The target sum for each part will be target equals 6. We initialize current_sum to 0 and parts to 0. As we iterate through the array, the first two elements add up to 6 at index 1. This matches the target, so we reset current_sum to 0 and increment parts to 1. Continuing the iteration, the next element, 6, also brings current_sum to 6 again. We reset current_sum and increment parts to 2. We then proceed to the subsequent elements, adding them to current_sum. For example, at index 3, the running sum is 5, and at index 4, it becomes 3, which do not match the target yet. As we continue iterating through the array, the running sum does not reach the target of 6 for several elements, including ARR 5 equals 2 and ARR 6 equals 5. However, at index 9, when we add 4 to the running sum, it finally reaches 6 again. This marks the third match. We reset current_sum to 0 and increment parts to 3. At this point, we have successfully found 3 parts where the sum equals the target. Finally, we check the parts variable and confirm that it equals 3. This means the array can be partitioned into 3 parts with equal sums, so the function returns true. The output for this example is true. The time complexity of this solution is O(n), where n is the length of the input array. To understand why, let's break it down into its components. First, calculating the total sum of the array using the sum ARR function takes O(n) time, as it requires iterating through all elements of the array. Next, checking if the total sum is divisible by 3 is a simple modulo operation, which is a constant time operation, O(1). Finally, the main part of the algorithm involves a single traversal of the array with a for loop. Within this loop, operations like updating the current_sum, comparing it to the target, and resetting variables are all O(1) operations. Since the loop iterates through the array once, it contributes O(n) to the overall time complexity. Combining these steps, the total time complexity of the solution is dominated by the O(n) operations, making it O(n) overall. The space complexity of the solution is O(1), which means it uses a constant amount of extra space regardless of the size of the input. Let's examine why. The algorithm uses only a few scalar variables, total_sum, target, current_sum, and parts, all of which take up constant space. Importantly, it does not rely on any additional data structures like arrays, hash maps, or stacks to process the input. This lack of size-dependent allocations ensures that the memory usage remains fixed, even as the size of the input array increases. Therefore, the space complexity is O(1). Let's now compare this approach to a brute force or naive method. In the brute force approach, we would attempt to check all possible ways to partition the array into 3 contiguous parts, verifying if the sums of each partition are equal. This would involve iterating over all potential partition points, leading to a time complexity of O(n², or worse, depending on the specific implementation. Additionally, such an approach might require extra space to store intermediate results, which would increase the space complexity. In contrast, the current approach significantly improves efficiency. The time complexity is reduced from O(n² to O(n) by using a single pass traversal and simple arithmetic checks. Furthermore, the space complexity is optimized to O(1), as no additional memory is used. This makes the current approach both time and space efficient. Now, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best-case scenario, the array can be divided into 3 equal parts early on during the traversal. For instance, if the first 2 partitions are found quickly and the third partition is guaranteed, the algorithm still needs to calculate the total sum, making the time complexity O(n). In the average case, the algorithm will typically need to check most elements of the array to identify the 3 partitions, resulting in a time complexity of O(n). For the worst case, when no valid partition exists, the algorithm must traverse the entire array to confirm this and complete its checks. Even in this scenario, the time complexity remains O(n). Across all these cases, the time complexity is consistently O(n). Let's conclude with a mathematical justification for the big O notation used in this algorithm. The key operations include calculating the total sum of the array, which takes O(n), and iterating through the array, which also requires O(n). When we add these together, we get O(n) plus O(n) equals O(n). Since big O notation ignores constants, the overall time complexity simplifies to O(n). On the other hand, the space complexity remains O(1), because the algorithm does not allocate any additional memory that depends on the input size. The use of only a few scalar variables ensures the memory usage stays constant, regardless of the array length. Thus, the space complexity is O(1). When working on this problem, there are a few common mistakes to watch out for. First, always check if the total sum of the array is divisible by 3 before proceeding. If it's not, partitioning the array into 3 parts with equal sums is impossible, and you should return false right away. Skipping this critical step can lead to unnecessary computations and wasted effort. Another frequent error involves overlooking edge cases, particularly with arrays that have fewer than 3 elements. Since the problem explicitly requires 3 non-empty parts, such arrays should immediately return false without further processing. It's also essential to remember that the 3 parts do not need to have the same size, only their sums must be equal. Misunderstanding this requirement can lead to flawed logic. Additionally, be careful with how you reset the running sum when identifying valid partitions. Resetting it prematurely or under incorrect conditions can cause logical errors. Finally, avoid using nested loops to check all possible partitions. This approach has a time complexity of O(n², which is inefficient. A single-pass greedy approach is both faster and sufficient for solving this problem effectively. Now, let's focus on some key insights that are especially valuable in interviews. The core idea of this problem lies in recognizing that the total sum of the array must be divisible by 3. Once this condition is verified, the goal is to identify 2 partition points where the cumulative sum equals 1/3 of the total. This simplifies the problem significantly. Additionally, this is a classic prefix sum problem, so being familiar with prefix sums is crucial for crafting efficient solutions, not just here but in many other array-based problems as well. To optimize your approach, emphasize using a greedy method that allows you to find the two partition points in a single pass, balancing both correctness and efficiency. Interviewers often value candidates who can demonstrate this balance during problem solving. Also, be ready to address edge cases, such as arrays with all zeros, like 0, 0, 0, 0, or arrays that include negative numbers. These scenarios test your ability to handle unusual but valid inputs. This problem also shares similarities with other array-based challenges, which makes it useful to explore related problems for practice. For instance, LeetCode number 560, subarray sum equals k, and number 523, continuous subarray sum, both involve prefix sums and efficient subarray calculations. LeetCode number 724, find pivot index, and number 416, partition equals subset sum, also require understanding how to divide arrays based on specific conditions. Exploring these problems can deepen your understanding and strengthen your approach to similar challenges. As for alternative solutions, a brute force approach involves iterating through all possible pairs of partition points and checking sums. While simple to implement, this method has a time complexity of n squared, making it impractical for larger inputs. A more efficient alternative is the space-optimized prefix sum approach, where you calculate prefix sums on the fly using a running sum, reducing space complexity to 1, while maintaining a time complexity of n. Finally, though less common for this problem, a two-pointer technique can be useful in cases where the array is sorted or has additional constraints, offering another way to efficiently locate partition points. Great job! To wrap up, we summarized the key points from solving problem number 1013. This problem is a great example of using prefix sums to solve partitioning challenges efficiently. Remember to keep practicing similar problems to enhance your skills. Thank you for watching. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!